Okay, let's continue from where I left. So let's look at theorem of 2.5. If we let A be the standard matrix of a linear transformation. Of a linear transformation. Let's say T from Rn all the way to Rm. Then T is 1-to-1 if and only if every column of A has a pivot position. So we let A be the standard matrix. So if you remember how our standard matrix was, then if you reduce that matrix, then each column should have a, for it to be a 1-to-1, that each column should have a pivot position. So let's prove this one briefly. Okay, so if we have T of X to be equals to A of X. So T of X to be equals to A of X. For this X, which is in Rn, for X, which is in Rn, then T is 1-to-1 if and only if the homogeneous matrix equation has the trivial solutions only. Also, this happens if all variables in AX equals to 0 are the basic variables. Also, the first n variables in A and 0 are the pivot columns. The first variables n variables in AX equals to 0 are pivot columns, and also every column of A has a pivot position. Every column A has a pivot. So if you remember that onto, when you say onto, you say onto all the what? The rows have the what? Pivot position. So that 1-to-1, all the columns pivot position. Okay, let's look at an example of this. Just example number 3. So let's look at example 3. Let's see from Rn to Rm be the linear transformation such that TE1 equals to 1, 2, 4. TE2 equals to 1, 1, 2, and then TE3 equals to 0, 3, and 6. 0, 3, and 6. So that's the transformation. Actually, this transformation is from R3 to R3. So the transformation is from R3 to R3. Now, is T 1 to 1? Is T 1 to 1? If you see, let's say the standard matrix, the linear transformation. Now in our case from T3 R3 to R3, then T 1 to 1, every column has a pivot position. So always should be satisfied for it to be 1 to 1. So how can we solve this solution? So we write this in a standard matrix form, which the standard matrix form is, we know A to be equals to TE1, TE2, TE3, which is equals to 1, 2, 4, 1, 1, 2, and then 0, 3, and 6. 0, 3, and 6. So that's our standard matrix. Our standard matrix. So you can be given a question in an exam, then you're given those vectors there, and you're told to write the standard matrix. So this is the standard. Now from here, we now reduce this matrix. So we now reduce the matrix. We now reduce the matrix. Okay, so to reduce this matrix, then looking at the first entry in the first row is 1. So it is not 0, so we cannot switch. So we can actually reduce it like that. So to change the new R2, to get a new R2, then R2 minus 2 R1. To get a new R3, then R3 minus 4 R1. Minus 4 R1. So to reduce this matrix, so what you get is 1, 1, 0, and then 0, negative 1, 3, and then the last one there is 0, negative 2, 6. 2, 6. Now, again, we can reduce the last one here. So to reduce the last one, then to get the new R3, then it is R3 plus 1. Is it plus or minus? Minus 2 R2. 2 R2. R3. So finally, what we get there is 1, 1, 0, then 0, negative 1, 3, and then finally 0, 0, 0, 0, 0. So if you look at this, there's a pivot position here and a pivot position. So the two columns here have pivot positions. The third column doesn't have the pivot position. So it means that, so you can say the third column of A does not have a pivot position. So T is not 1 to 1. So T is not. Any question after that? Okay, let me leave you with example number 4. It is easy to check this. So it is the same way. So if you let T to be R3, from R3 to R3, be the linear transformation, such that TE1 equals to 1, 2, 4, TE2 equals to 1, 1, 2, and then TE3 equals to 0, 3, and 9. Is T 1 to 1? Is T 1 to 1? So the only thing which changed here is the last inch. So if you check that out, you realize that all the pivot position, all the columns have the pivot position. So it means it is 1 to 1. It is 1 to 1. So you can go check that. Okay, any question up to that? Okay, let's look at the next section, which is also the next chapter, which is 2.1. So let's look at 2.1. And this one is the matrix operation. The matrix operation. So this chapter, I think it will be easier. So after doing chapter 1, then I guess chapter 2 will be a little bit easier, and we might even go faster than what we've done in chapter 1. Okay, so the first section that we're going to do is the addition and the scalar multiplication for matrices. Addition and scalar multiplication. Okay, so let's define something here. Definition, what is a matrix? If we let A and B be M by N matrices, and R be a number, which can be a real number, then so if A is an M by N matrix, so if we have our A, so for this A to be an M by N matrix, then the first entry is A11, the next one is A12, and then it goes all the way to A1, and A21, A22, and then it goes all the way to A2. So if we continue like this, then it is AM1, AM2, and then it goes all the way to AMN, AMN. So this is like that, this one is like that, this one goes like that. For B, then it is the same thing. So B11, B12, all the way to B1N, B21, B22, all the way to B2N, and then BM1, BM2, and then it goes all the way to BMN. Now, if we add the two matrices, then A plus B is similar to adding the two of them. So we add each of the entries. So A plus B, since this is m by n, then we are able to add this n plus this, not even plus. So the next entry is this and this. The next one is like that. So A plus B, what we get here is A11 plus B11. The next one is A12 plus B12. If you continue like that, then the last one is AN1 plus B1N actually. 1N. 1N. A21 plus B21. A22 plus B22. And then B2N plus, or A2N plus B2N. If you continue like that, then AM1 plus BM1, AM2 plus BM2. And then the last one is AMN plus BMN. So when you add that much, so you add each of those entries, Now, if we multiply by R, let's say RA, if R is a number, then RA is similar to R, and then you multiply by A11, A12, A1N, A21, A22, A2N, AM1, AM2, AMN. So if we multiply by R, then you multiply each entry by R. So this is equals to RA11, RA12, RA1N. So if you continue like that, then RAM1, RAM2, RAMN. So is. So you multiply each entry. Now, let's look at the remark. The negative matrix A or of A is defined as negative A, which is similar to -1 and then A. And that -1 can be what? It's the same as so you multiply each into there by negative. So another remark, number 2, the matrix subtraction is just similar to matrix addition. Is defined as A minus B, which is equals to A plus -1 and then so you can multiply -1, or you can change B given negative matrix, and then you add the two matrices. Add the two matrices. And then the last remark, number 3, we usually use 0 to denote a zero matrix. We usually use zero to be a zero matrix. That means all the entries are zero. It means all the entries are zeros. All the entries are zeros. Now, let's look at a very simple example on matrix addition and scalar multiplication. Okay, example number 1. Find 2a minus 3b and 2a minus 3b, where a equals to 2, 0, -1, 4, -5, 2, and b equals to 7 minus 5, 1, 1 minus 4 minus 3. Find 2a minus 3b. So actually, this is similar to, so to get now 2a minus 2b minus 3b, then this is the same as 2 multiplied by 2, 0, -1, 4, -5, 2, minus 3 multiplied by 7 minus 5, 1, 1 minus 4 minus 3. So we can distribute that. So this is just similar to we can now distribute it inside there. So this is equals to 4, 0 minus 2, 8 minus 10, and then 4 minus. We distribute 3, so 21 minus 15, 3, then 3 minus 12 minus 9. And then we solve now this. We add the two matrices. So when we add, then what do we get? So we get minus 17, and then we have 15, and then minus 5, 5, 2, and 13. Okay, let's look at section 1.2, properties. So let's look at properties. We let the matrix A, B, and C be matrices of the same dimensions, and R and S be numbers. R and S be numbers. Then property number 1. When you add A plus B, then it is similar to adding B plus A. So long as the two matrices are of the same dimension, then they can commute. They can commute. So you can either add A plus B, or you can say B plus A. B plus A. They are similar. Number B, if we add A plus B plus C, it is similar to A plus B plus C. So we can add A plus B and then add C, or we can add B plus C and add A. So they are similar. They are similar. So they are associated. Number C, A plus 0 matrix is the same as A. So if all the entries are 0, then when you add by matrix, then you get the same matrix. Let's see. A plus negative A is similar to 0 matrix. So if you add the addition identity of the inverse, then you get the identity. So the inverse of a positive is a negative. So if you add the two of them, then you get a 0 matrix. Number D, if we multiply R by A plus B, it is the same as distributing R in A plus R. Distributing R in each one of them first, and then add. Then number F, if you have the two numbers R and S, and then you multiply by a matrix, you can actually add the two numbers, then you multiply by a matrix, or you can distribute the matrix in each one of those numbers, and then you add. And then number G, we have S, R, and then S, and then A. Then it is similar to multiplying RS first, and then you multiply by matrix A. And then the last one, by H. If we have the identity, which is, let's say, 1, and then you multiply by A, then it is the same as it is A. You remember the identity. You multiply identity by matrix, then you get the same matrix. Okay, let's look at section number 2. In this section, the multiplication for matrices. Multiplication for matrices. So when we multiply two matrices, so what are the properties of multiplication? So let's define this multiplication of the matrix. So let's look at definition. Now, if we let A be an M by N matrix, and our B be an N by P matrix. We let A to be M by N matrix, and B be an N by P matrix. If we define the transformation from Rn to Rm by Ay equals to Ty. Ay equals to Ty. Or we can say Ty equals to A, Ty equals to Ay. We define that Ty equals to Ay for Y, which is now in what? In this what? In Rn. For Y in Rn. For Y in Rn. And S to be the transformation from Rp to Rn. Rp to Rn. This is now for B. by S, let's say X equals to BX for X element of RP, for X element of RP, for X element of RP. Then both T or S and T are linear transformations. So the composites of S and T is a linear transformation also, whereby the T of S is transforming from RP to RM, from RP to RM. T of S is transforming from RP to RS, which is given by T of S of X, which is equals to transformation of S of X, transformation of S of X for X element of R, for X element of R. T of X is transforming from R to R. Equals to. Now, the standard matrix T of S, which is written AB, is called matrix multiplication of A by B, which is M by P matrix, which is M by P matrix. This is a lot which you don't have to remember. The only thing you need to remember is when you multiply the matrix, you can say M by N, and then you multiply by the matrix and N by P. So in this case, if we have, let's say, this matrix here, let's put it like that. And this one is M by N, and this is matrix A. And we have this matrix B, and this one is P by, so let's say N by P, okay? Then what you should get is a matrix AB here, right? The matrix AB. And this matrix should be M by what? M by P. M by P. So in this case, for this matrix to multiply, then the number of rows, sorry, the number of columns of this A should be equal to the number of rows to know. So that one too. Else it will be n. So the number of columns here. So if you take one entry here, multiply by one entry here, take another one, multiply by the one which is here, like that. So that means the number of columns here should be equal to the number of rows. So therefore, we have these matrices M by N, this one by N by P. Looking at this, number of columns is equal to the number of rows. Okay. So this m can be equal to this m. So therefore, this now will now be m by what? Matrix. So let's look at the remark. Number one, the matrix product AB is defined only if the number of columns in A is equal to number of rows in B. Number two, we write B to be equal to the linear combination, which is B1, B2, all the way to, let's say, BP. And let's X to be equals to X1 all the way to XP. And these are elements in RP. Elements in RP. Then T of S of X is similar to of S of X. T of S of X. Yeah. And this S of X, so it is now equals to T of this S of X is equals to what? B of X. T of B of X. That S of X is the same as this S of X. This is equal to B of X. So then this is similar to T, and then the linear combination now of B of X, which is from here, which is the same as X1 B1 plus X2 B2 plus all the way to plus XP BP. XP BP. Now, when you now put back the transformation there, when you put T inside, then this is equals to X1 T of B1 plus X2 T of B2 plus XP T of B. Now, then we can write this in matrix form. So when we write this one in matrix equation form, then what do you get? So this is similar to TB1, TB2, all the way to TBP. And then multiply by the vector X. Multiply by the vector, right? And basically, this is the same as what? This is the same as multiplying A B1 A B2 all the way to A B multiplied by what? X. Therefore, then so A, B is the same as AB1 all the way to ABP. So that is our matrix. Any question up to that? Okay, let's look at example number 2. If we let A to be equals to 1, 2, negative 2, 1, and our B to be equals to 2, 0, negative 1, 4, negative 5, 2, then find AB and BA if defined. If defined. AB and BA if defined. Now, to get now AB, then it is similar to multiplying 1, 2, negative 2, 1, multiplied by 2, 0, negative 1, 4, negative 5, and 2. Is this defined? Is the number of columns in A equals to the number of rows in B? It is, right? So it is defined. So this is equals to multiplying 1 and 2 plus. So 1 multiplied by 2 plus 2 multiplied by 4. Or let's define another way here. Using this property here. Using this one here. To get to multiply A by B, then what you do is you multiply the matrix A by B1, which is the vector B1, matrix to get the next column like that. So to get our AB here, we will name this one as B1, and this one as B2, and this one as B3. Then to get AB in this case, then our solution here will be A, B1. The next column is A, B2. And then the third column will be A, B3. A, B3. Now, to get A, B1, then it is the same as multiplying the matrix 1, 2, negative 2, 1 by the first column, which is 2, 4, which is equals to AB2 is the same as multiplying 1, 2, negative 2, 1 by 0, negative 5. And then to get AB3 is similar to 1, 2, negative 2, 1 multiplied by negative 1 and then 2. 1 and 2. Okay, so that is how we multiply. So here, now take the way we were multiplying the matrix by vector. Then is 1 multiplied by 2 plus 2 multiplied by 4. So 1 by 2 is 2, 2 by 4 is 8. So the first one there is what? 10. 2 by 2 is 4 minus 4, and then 1 by this is 4, you get 0. This by this is 0, 2 by this is minus 10. This by that is 0, this by that is minus 5. This by this is negative 1, 2, and 2, you get here 3. And then this and that is 2, and that you get here 4. Get 4. Now, AB will now be bringing back these matrices here: 10, 0, -10, -5, and then lastly 3 and 4. So that is now. What about BA? BA is multiplying B, which is 2, 0, -1, 4, -5, 2, multiplied by 1, 2, -2, 1. Looking at this, are the number of columns in B equal to the number of rows in A? No, right? So it means that the matrix BA is undefined. The matrix BA is undefined. Any question after that? Any question? We have 3 more minutes, so let's do something small. 2.2. Now let's look at the row column rule. If we still remember the row column rule here, similar to this. So if we have A is an M by N matrix, and our B N by P matrix, then the IJ entry in the matrix product AB is given by how AIJ or AI1. Let's start from AI1. B1J plus AI2 B2J plus AIN BNJ. Then this is equals to same as adding K equals to 1 to N AIK BKJ, where I is equals to 1 to all the way to M, and J is equals to 1 to all the way to P. So when we meet, we will discuss about this and we look at an example. Okay, we will meet on Wednesday. On Friday, I mean. So I'm still grading your homeworks. If you have an issue, your grade, do you guys need the solutions for the homework? Yeah. Okay, I'll post them.